Modern enterprise networks require redundant physical links to stay online. If one cable fails, another must be ready to take over immediately. But mathematically, that exact physical redundancy guarantees total network collapse without a regulatory algorithm. To understand the mechanism behind this, we have to look at how Layer 2 switches operate. When a switch receives an Ethernet frame bound for an unknown destination, it uses a mechanism called flood and learn. It copies that frame and sends it out of every single port except the one it arrived on. Let's apply that behavior to a closed-loop topology of 4 switches. A server connected to switch A transmits a single broadcast frame into the network. Because Ethernet frames operate at Layer 2, they lack a time-to-live header. There is no built-in expiration mechanism to discard wandering packets. Switch A floods the frame. The copies hit switches B and D, which dutifully flood them again, sending them right back toward each other and back to switch A. This creates an exponential feedback loop. Within fractions of a second, thousands of duplicate frames circulate indefinitely. This is a broadcast storm, and it instantly consumes 100% of the available link bandwidth. The hardware itself begins to buckle. As the identical frames arrive from multiple directions, the switch's CPU tries to map the sender's MAC address to different ports in rapid succession. This process, known as MAC flapping, paralyzes the control plane. In a purely physical Layer 2 environment, a single misconfigured cable connecting 2 switches twice acts as a self-inflicted denial-of-service attack. In 1985, an engineer and mathematician at Digital Equipment Corporation named Radia Perlman was tasked with solving this exact problem. Her solution was the spanning tree algorithm. The algorithm's primary mathematical objective is straightforward. It takes a complex, physically meshed network containing cycles and maps a loop-free logical tree structure over it. It achieves this by calculating a single optimal path between all points on the network. Any redundant physical links that create loops are forced into a dormant, non-forwarding state. Perlman designed this as a distributed computation model. There is no central controller dictating the layout. The switches communicate peer-to-peer, sharing information to collectively derive the topology. The spanning tree protocol allows physical redundancy to exist. The extra cables remain in place as an automated backup, ready to activate if a primary link fails, without triggering a network-killing broadcast storm. Let's reset to our 4-node topology to examine how this distributed decision is made. The absolute first step of the algorithm is to elect a root bridge. When the network powers on, every switch blindly assumes it is the root bridge. They immediately begin transmitting Bridge Protocol Data Units, or BPDUs, to their neighbors to announce their claim. The election is settled using an 8-byte metric contained within those packets, called the bridge ID. This ID is split into 2 parts, a 16-bit bridge priority field and the switch's hardware MAC address. By default, the bridge priority is set to 32,768. Network engineers can manually configure this value in increments of 4,096 to dictate which switch wins, with the increments accommodating specific VLAN identifiers. The logic of the election is absolute. The switch broadcasting the numerically lowest bridge ID wins the title. If an engineer leaves all priorities at their default settings, the tie is broken by the hardware itself. The switch with the numerically lowest factory MAC address is elected root bridge. This elected root bridge becomes the absolute logical center of the network. Every other calculation and path cost will be measured directly from this specific point. With the center established, the algorithm enters its second phase. Every non-root bridge must now map out its best route to reach that root bridge. They do this by calculating the root path cost, which is the cumulative sum of the link costs between the current switch and the root bridge. This chart details STP cost values. Path cost is inversely proportional to link bandwidth. A legacy 10 megabit copper link carries a massive cost of 100, while a 10 gigabit fiber optic link drops the cost all the way down to 2. Each non-root switch evaluates its available paths and selects a single interface that yields the lowest cumulative cost. This specific interface is designated as the root port. Next, the network must manage the individual segments. On every collision domain, or link connecting 2 switches, exactly one interface is elected as the designated port, tasked with forwarding traffic toward the root. That brings us to the final, critical step. Any interface that fails to earn the title of root port or designated port is forcefully transitioned into a blocking state. It drops all standard user data, only listening for incoming BPDUs. By forcing these suboptimal ports into a dormant state, the algorithm mathematically severs the loop. The broadcast storm is prevented, while the physical cable remains continuously monitored and ready. While the original 802.1d standard solved the redundancy paradox, it contained a critical flaw for modern environments: unacceptable convergence delay. The original protocol relied entirely on passive conservative timers. These timers were based on maximum network diameter calculations, implemented to guarantee all switches had an identical view of the topology before any data forwarded. This chart illustrates the original transition timeline. A switch port spends 20 seconds waiting for a max age timer to expire, followed by two 15-second intervals progressing through listening and learning states. That meant a full 50 seconds of dead air before traffic resumed. As enterprise reliance on network uptime increased, a 50-second outage was no longer viable. The Rapid Spanning Tree Protocol, standard 802.1w, abandoned passive timers completely. RSTP uses a proposal and agreement mechanism. An upstream switch sends a proposal. The downstream neighbor executes an active handshake, aggressively syncing its ports and instantly blocking redundant paths. It fires back an agreement, dropping convergence to mere milliseconds. By shifting from passive observation to an active handshake, the switching infrastructure can heal physical failures faster than applications or servers time out. As networks expanded, virtual LANs introduced a new scalability bottleneck. If an entire network containing hundreds of VLANs follows a single common spanning tree, all traffic is forced down identical paths, leaving redundant bandwidth sitting idle. The alternative is equally problematic. Calculating a distinct, isolated spanning tree instance for every individual VLAN demands continuous calculation, mathematically overwhelming the processing power of the switch CPUs. The Multiple Spanning Tree Protocol, or 802.1, optimizes this. MSTP allows engineers to group multiple VLANs into a small number of shared spanning tree instances, enabling deterministic load balancing without exhausting hardware resources. Yet, regardless of the version running, the protocol shares a critical vulnerability. It operates on complete trust. If any device is plugged into a port and transmits superior BPDUs, it will usurp the root bridge role and redraw the entire topology. To harden the network edge, engineers employ a suite of security features known as the STP toolkit, heavily relying on safeguards like root guard and BPDU guard. BPDU guard protects user-facing access ports. If a switch receives a BPDU on a port where only a standard computer should be connected, the port instantly flashes red and shuts down, placed into an air-disable state. The core protocol functions on the assumption that all connected devices are compliant switches. Network administrators must explicitly program these security boundaries to ensure the topology survives in an unpredictable human environment. In massive modern data centers, STP's core mechanism hits a physical limit. Because it blocks redundant links, it actively prevents the active-active multipathing required for the immense throughput these facilities demand. To utilize all available physical paths simultaneously, engineers have shifted toward overlay networks like VXLAN and routing protocols like TRILL. These technologies encapsulate Layer 2 traffic within loop-free Layer 3 packets, bypassing the redundancy paradox entirely. However, despite the deployment of overlay fabrics and software-defined networking, the spanning tree protocol has not been retired. It continues to run quietly at the network access edge. When a rogue cable is looped under a desk or an unmanaged hub is connected to the wall, STP serves as the essential automated loop detection mechanism of last resort. STP remains enabled by default on nearly every piece of networking hardware sold today. It persists because it manages the one variable that software-defined fabrics cannot: the physical mistakes of the people using the network.